Should we wait for the elephants? Here come the elephants. Yeah, so yesterday was all about these 4 rules, but what you really needed to remember is not so much the 2 on the left, but the 2 on the right. So to the u is e to the u prime, and then the derivative of ln u is 1 over u times u prime. And then somebody says to me, Mr. Can I write this? And I said, you betcha, sister. So, don't remember those. Those are nice, but I would just, those are the 2 you need to know. Okay. Log rules. Do we need to do those? Ln x equals y is the same as x equals e to the y. One's logarithmic form, the other one's exponential form. ln1 is 0, ln e is 1. What else do we need to know? ln e to the x is x ln e. So it's just x. Is the answer to the one on the right any different? Same thing. ln ab is the same as ln a plus ln b. Pardon me? Why are we doing natural logs and not regular logs? Because the derivatives of natural logs are so much easier than derivatives of regular logs. It's actually easier. It's not natural because you guys are not, Mr. F, I don't like using a base of e, but the derivatives are beautiful in a mathy sort of way. Mr. F, we've seen these, right? I'm so tempted to just not do these anymore. Log a of b is the same as ln a over ln b. So it's just the log rules written with ln's rather than log base, whatever you want. ln a over ln b. Yeah, log a over log b. Okay, you guys are so used to base 10. Calculus, you don't want to work in base 10. Base 10 sucks. So it would be log a over log b in base 10. Mr. Up, you can use any base. Oh, yeah, right. So you can put anything here in the yellow circle. So I put little e's in the circle, which is ln a over ln b. As long as you put anything in that yellow circle, as long as it's not 0 or 1, it's good, right? So, Mr. F, if I wanted to create my own special number, I don't know, zeta, and it has a really cool property, you could do log base zeta of A over log base zeta of B. It doesn't matter. You could have your own symbol, Liz, and that would be log base zeta. No? Okay. Okay, logarithmic differentiation. So, why we do this. Stop moving, page. We use logarithmic derivatives for 2 different reasons. 2 different reasons. Reason number 1, you have a variable in base and exponent. So if you're working on a problem that's got a variable in the base and in the exponent, you need to do logarithmic differentiation. You have to. And you're like, what's logarithmic differentiation? You'll find out in a second. The other time you use it is, I am too lazy to use the product rule and or the quotient rule and or the chain rule. When you're too lazy. Seriously. Too lazy or too complicated to use chain, product, quotient, rules. I'm going to give you an example of that. Like, there's enough room on the bottom of this page where I'm going to give you a really good example of you can say too lazy, but it's too complicated. Yeah. The simple ones, I would expect you to use the product rule or the quotient rule. But the not simple ones, I would expect you to do it this way. So, like, it'd be multiple choice, and if you use logarithmic differentiation, the answer won't look immediately like the way you want it to, so you'd have to do a pile of work to get it to look like one of the multiple choice answers. Okay. This is more, 2 is more like, I'm going to tell you to use logarithmic differentiation. Okay. The AP exam does. I looked last night, I was looking at a sample exam, and I was like, oh, cool. So it tells you, use logarithmic differentiation. You look, I mean, it was so obvious that you had to, but so first thing you need to do is to log both sides. So ln y equals x l. Oops, this rep already wants to skip steps. Ln x to the power of x. So you just log both sides. You can already know what you're going to do because I started to give it away. X ln x. ln y. Okay, take the derivative of each side. So we take the derivative of each side and we get 1 over y times y prime equals. Thank you, yes, here. Product rule! Yeah, I read your lips. That's what you said. U equals x, u prime equals 1, v equals ln x, v prime equals 1 over x times the derivative of x. So, put it in the product rule. Derivative of the first times the second plus the derivative of the second times the first. Now what? Yeah, sort of. Would we agree to that? Okay, we want y prime equals. Who's got to move? The y. This has got to move. So you get y prime equals bracket ln x plus 1 bracket times y. Hey, Mr. Rat, I know what y is. It's what's y? There you go. And you're finished. I should zoom out so I can make that highlighting reference. You're just going to take... Okay? So, when you have variables in the base and in the exponent, you need to use logarithmic differentiation. You have no choice. None. Okay? If you attempt to do this, I'm going to laugh at you and just put 0 on your page. Y equals x to the x. So you do something like, oh, cancel. What? Why is it doing that? Cancel. Why are you doing to me this morning? No, we'll write it right here then. Hopefully it doesn't crash. If you do this, I don't even know how you would. I don't even know how you would do that. Anyways, Okay, the other time you use logarithmic differentiation. There you go. Mr. App, when I say the derivative of the top, you're going to have to use the product rule. So can you see why I mean say too complicated? Okay. So what you need to do here, and we're going to first couple of steps of this, and you're going to go, okay, I see it, how it works. So the process is exactly the same. What you need to do is to just ln everything right away. So you get ln y equals ln, now watch, I'm going to use my log rules, and this is why we talked about them. Ln root x plus 5 plus ln x squared plus 6 to the power 3 minus ln x minus 1 to the 4th power. Multiplication is addition, division is subtraction. Yeah? Then you can use the power rules for logarithms. 1/3 ln x plus 5 plus 3 ln x squared plus 6 minus 4 ln x minus 1. Anybody know the moral to the story now? I'm getting one head nod. Mr. App, continue along the process. No. We haven't taken the derivative yet. Okay, so the process now is exactly the same as the one on the left. 1 over y times y prime, and then you just start taking the derivative of each of the pieces. 1/3 times 1 over x plus 5 times the derivative of x plus 5, 1, plus 3 times 1 over x squared plus 6 times the derivative of x squared plus 6. Minus 4 times 1 over x minus 1 times the derivative of x minus 1. 1. There's way more derivatives to do, yes, but they're all little easy ones. All little easy ones. So when you get to the step, when you go from this line to this line, if you don't have a bunch of tiny little easy derivatives, you've done something wrong. Well, I know, easy with quotes around it, right? No? Because you're finished. Y prime equals bracket 1 bracket plus 6x over x squared plus 6 plus minus 4 over x minus 1 times y, which is that thing up there, which is huge, but it works. That's the derivative of it. Yeah, you would then just copy it in. Yeah, no, it's always just your first line. Yeah, no, that's when we were doing y double prime. No, I am not going to make you do y double prime of this. Yeah, implicitly? Oh yeah, y double prime for sure. I mean, if I give you a position function, I could ask you the acceleration. So yeah, I guess, yes, I can, and I will ask you about y double prime of things. What? It is messy, but it's not that bad, right? Could you imagine what it would look like if you used the product rule with the quotient rule? Would you like to do it that way? And have I convinced you that maybe logarithmic differentiation, while messy, is easier when you've got ugly looking derivatives? Okay. Flip page. So find the derivative of 3 to the x. Now I don't give you the rule for 3 to the x. I'm going to make you generate the rule. So the only thing you know how to do when you've got the variable up in the exponent is to log it, ln it. So ln y equals x ln 3. I skipped a step. Is that all right? Take the derivative left-hand side. One over y times y prime. Take the derivative of the right-hand side. Now this is where kids get really freaked out. What's the derivative of 2x? 2. What's the derivative of 5x? 5. What's the derivative of ln 3 times x? ln 3. ln 3 is a constant, like 5 or 2. You need to see this as the same as these. Yeah, there it is. Yeah. 2x and x times 2 is the same thing. It's just you guys are so programmed into. Okay, so I'm gonna pretend that you guys didn't say this to me. You guys are gonna go, Mr. F, I'm gonna use the product rule. U equals x, u prime equals 1, v equals ln 3, v prime equals 1 over 3 times the derivative of 3. And then you put it together using the product rule. Derivative of the first times the second plus the derivative of the second times the first. What do you get? ln 3. But why wouldn't you just do this? Because it's easier. But you need to see ln 3 as a constant, is a number. If you don't believe me, type ln 3 in your calculator 4 or 5 times and see if it changes in value. It's a joke, folks. Does it change? Type it in now and then maybe at 3 o'clock and then maybe tomorrow at 7 a.m. See if it's changing in value. ln 3. It's about 1 point something. 1.5-ish? Okay, so 1.098. John, type it in your calculator. See if it changes in value. Maybe it's dependent on the calculator that we're using. No, it's the same? Okay. Anybody else want to? Mitch, does it change on yours? No. Okay, so are we agreeing that ln 3 is a constant? Yes? Okay. This is called overkill. Okay? Okay. So the derivative of this is ln 3 times y. Well, what's y? 3 to the x. So ln 3 times 3 to the power of x. So you've now created a new formula for the derivative of a to the x. What is the derivative of a to the x? ln a times, a to the u. ln a times a to the u times u prime. Because u is a function, yeah. Chain rule. That's the chain ruled version of the derivative. So using the algebra of logarithms, at what point does the graph of a function, does the tangent line do what? Have a slope of 21. Okay, so at what point, so we're looking for x comma y here. Does the function have a slope of a 21? So slope means derivative. So y prime equals, take the derivative of 2 to the x minus 3. ln 2 times 2 to the x minus 0. So has a slope of 21. 21 equals ln 2 times 2 to the x. Okay, now it's a math 12 question. Solve for x. Divide both sides by ln 2. So 21 divided by ln 2 equals 2 to the x. Get the x down from there. What log? What base? ln, because we're on a roll with it, and we might as well use it some more. Okay, ln bracket 21 over ln 2 bracket equals x ln 2. Now what? Yeah. ln 21 over ln 2 all over ln 2. I'm thinking calculator question extraordinaire, right? So ln 21 divided by ln 2 close bracket divided by ln 2. 4.92. So x equals 4.92. Y equals, what's the equation of this bad boy? 2 to the x minus 3. 2 to the answer, 2 to the answer minus 3. 27.3. Yeah. If you don't believe me, what do? Graph it in the calculator. Use the second trace. dy over dx. Hit 4.92. Enter. It should give you a number close to 21. Yeah. If you don't believe me, check it out. Okay, flip the page. So, change the exponential form and differentiate implicitly. Okay, so Mr. App looks at that and goes, yeah, I don't have any rule for log base a of x. So what I would like you to do is to get rid of your logs. A. So you get a to the y equals x. Okay, what's the derivative of a to the y? You just did it. What? ln a times a to the y times y prime equals, take the derivative of the right hand side, 1. Okay, make it y prime equals y prime equals 1 over ln a times a to the y. Everybody know what a to the y is? What is it? X. Take a look at this. A to the y equals, oh yeah, it's right here. I'm stupid. I'm overkilling it, and you guys are doing it fast. Anybody know what a to the y is? It's x. I guess we should write it like that, so you don't assume that the a and the x are being multiplied together. It's ln a times x. So, formula number 1 over, and I write it a little bit differently. I write it as x ln a. I like the variable first here, just so I don't get into that habit of multiplying the a and the x together. So, when it's u, it's going to be 1 over u ln a times u prime. Now, I put it out there over on the side, but you could also just put it on the top of the fraction if you want. So you could write it as u prime over u ln a. Okay? So, find the derivative of each of these bad boys. So, okay, ln x squared, I don't know why this one's here, but okay, ln x squared is, you guys can spit this one out at me fast. Y prime equals 1 over x squared times 2x, and then I heard somebody simplify it, 2x over x squared, yes, which is the same as 2 over x. B, log base a of x squared. Over x squared times ln a times 2x. And if you want to simplify it, y prime equals 2 over x ln a. Okay, what about C? I gotta yoink. What? E to the sine x times cos x. Good. E to the u times u prime. D. Oh, I know why. These are the old ways, old school. The easier ones, and then over on the right, these ones are new school. So, 5 to the sine x. A to the u times ln a times u prime. A to the u, 5 to the sine x, times ln a, ln 5 times u prime cos x. What? It's just the rule from the previous page. If you start with y equals a to the u, its derivative is, I've remembered it this way, a to the u ln a times u prime. We wrote it as ln a times a to the u times u prime. I've just flipped the order around because that's just the order I've memorized it in, but as long as you memorize that all three pieces need to be there, does it really matter? Test, does it really matter? No. Or does it matter when you multiply? Well, order in this doesn't matter. You guys hate when I do that, I'm thinking. Okay, y equals x to the sine x. This must be like the last one on this column. It is. It's very exciting. What do we have to do? Ah, gotcha. What? What do you do when you've got a variable in the base and in the exponent? You must log it first. Grumble, grumble, grumble. ln equals sine x times ln x. You must log it right away. Sorry, kids, no choice. U equals sine x. V equals ln x. U prime equals cos x. V prime equals 1 over x. So you get 1 over y times y prime equals what? Cos x times ln x plus sine x times 1 over x. So y prime equals, open a big bracket, and y is so whenever you have a variable in the base and in the exponent, you must, shall, no choice, log it first. Okay, one on the right. X to the pi, pi to the x, x to the x. Pardon me? So, do you want to do this by logging everything? No, we don't want to log everything right away. It's not going to help you. What's the derivative of x to the pi? Pi to the x to the pi minus 1. What's the derivative of pi to the x? Pi to the x times ln pi times times 1. What's the derivative of x to the x? You've done this somewhere else in your notes. Go look. Bracket ln x plus 1 bracket times x to the x. Now you're looking at this going, OMG, what just happened? You need to see, the reason we did this example is you need to see this is the same as that. You need to see those is the same. That's really why I did that example. You need to see that they're different because their derivatives, when you take them, are not the same thing, right? Don't forget that when the variable is in the base, you just use the power rule. But when the variable is in the exponent, you need to be more careful. You need to use logarithms. Okay? It's something to get caught up on easily, to form that bad sort of meaning. Yeah. I'm just saying that the example I just asked you and the one down below, most kids can look at this and say, yeah, I can see that the derivative of the yellow circle of x squared is 2x to the 1. But when I give you this pi, x to the pi, for some reason you get freaked out. Well, x to the pi. Haven't you noticed I've already started to do that with you on those assignments? I had, I don't know, pi x squared times e, you know, all that crap. Didn't you notice that I was doing that already to get used to the idea that pi and e are just constants? Okay, so I'm just trying to reinforce that. So pi x to the pi minus 1, and then the other one is pi to the x. When you do that one, you need to make sure that you're recognizing that the x is in the variable, or in the exponent, so you have to use a different rule. Okay, anything on the next page? A line with slope m passes through the origin. Okay, what's the origin, kids? Good. And is tangent to the curve of the graph y equals ln x. Tangent to the graph. Okay, tangent. What do you think when you hear the word tangent? Slope. And what do you think when you think slope? Derivative. Y prime equals 1 over x. So I am looking for a line with slope m. So what we're saying here, what is the value of m? S plus x. So this line, a line with slope m of the origin. Y minus 0 equals m x minus 0. So what I'm asking you to think about is this. I want to know where that what value of m will do that for us. What? I can't. You want to close the door. It's getting a little bit loud. So I need you to strategize how we're going to find that. Maybe not that point, but how we're going to find. Say that a little louder. That might work. But I was just going to... Okay, so let's just have a visualization of what's going on here. Because I didn't tell you where it's tangent, did I? So you could write, like, we could just write y equals x and y equals ln x. Are they tangent? Do they even touch? So m isn't 1. Would you agree to that? Okay, I'm trying to put 0.5 here. Oops. I'm an idiot. Better? Well, how do we know where those two lines cross? What? Yeah, but... Okay. Well, how about just doing this? How do we know if these two lines cross? One equals the other one, right? Well, that's trial and error, but what I'm trying to get you to think is maybe think a little bit algebraically. Well, how do you solve this? I'm going to get a formula with m in it. You guys don't want to do that. Well, how do you... could you do this? I don't know. Yeah, I know. I want m equals. Why don't we just m equals? M equals ln x over x. Would you agree to that? No, I don't know. Well, we know that curve intersects at that point. I don't even think we need to care. I think it's just what's the value of m? M is the value is ln x over x. Isn't it? It says what is the value of m? M is ln x over x. I don't even think we need to know the derivative. Unless and then m equals 1 over x. So we get an equation that looks like this. 1 over x equals ln x over x. Oh, I see what's going to happen now. So good, somebody referred me. Hey, look at the derivative, silly. Okay, solve this equation for x. So I would clear my denominators. And you get x over x equals ln x. What's x over x? 1. Get rid of your ln. E to the 1. So x equals e. 2.71812, and like it doesn't change in value. So you know m now. M is ln e over e. What's m? 1 over e. That's kind of cool. Okay, so let's zoom out. So this is what I mean by a true problem-solving activity. Every year I've kind of avoided this question because I was like, yeah, whatever, nobody's doing AP. Now I sat back and I actually strategized. I graphed it. I took a look at what was going on. I went, geez, this is going to take way too long to figure out this. Like, imagine guessing checking every single value of x so that when they'd only intersect at one point and they'd be tangent right there. Anybody want to try an infinite number of values of m to do that? No. So what I sat back and I said, okay, well, if the slopes are equal, so mx equals ln x, okay, we can make it m equals. That tells us something. Oh, yeah, right. And then I went, the derivative of ln x is 1 over x. And then because they both represent slopes, they have to be equal to each other. Like, be willing, not so much on this test, but as you get closer and closer to the AP exam, be willing to try things. Yeah, these are both y values. These are both y values. Y on the ln graph and y's on the mx graph. Yeah, it does. It does. Because if you divide both sides, if you solve the equation for m, I'm going to stop recording.